Okay, so now in this video, I'm going to show you the next step in the derivation of the formula. So we've got the formula here, so now we're going to try to put this in terms of functions and for the curve, okay? So, here's a sideways view of the cone, right? So here's the slant length, right? And here's the base radius, and here's the other radius. So you could look at this as R1 and R2, right? So R1 is this distance here, right? So let's say we're rotating it around this axis. Then the radius is just the distance from here to here, which is just this value, this function. And this radius here is just the distance from the x-axis to this function, right? So we could replace R1 and R2 with f of x sub I plus f of x sub I minus 1. Okay? And then, now what about the L? Well, that's the slant length of this part of the cone. But that's just the arc length, right? That's what we did with arc length. So L we can replace with what we had before, which is going to be the square root using the Pythagorean theorem of delta, what is it? It's delta x. So delta x, not A, come on, Mark. So delta x squared plus delta y sub I squared. Okay, so remember, this is just what we derived before for arc length. And now, we can rewrite this, again, I'm going to flip these around, the addition doesn't matter, but we can rewrite that too, remember? So we had pi, and we'll write this as f of x sub I minus 1 plus f of x sub I. In fact, let's put square brackets. And now I'm going to divide and multiply by delta x squared. And I'm going to rewrite this. So we're going to pull out the delta x squared. Or no, delta x. We're going to pull out the delta x. And what's left in the parentheses, or excuse me, I'm sorry, under the radical is going to be 1 plus the quantity delta y sub I over delta x quantity squared, which you saw before. Now, just like we did before, we're going to apply the mean value theorem to select delta x sub I star in each one of the subintervals. So, again, we're going to replace this with a value of the function based on the mean value theorem. So remember, in each subinterval, we know that there's some point in the subinterval where it's going to have the same slope. And so we can replace this with the derivative again. So just like we did before, this is the same thing. So we're going to replace Okay, so we're going to replace it with, oh, and these as well are going to be x sub i's as well. Okay. So let's do that. I'm running out of room and I will. So let's do that. I'm going to erase some things just so I can put it there. So based on the mean value theorem from before, so we're going to replace delta x with the derivative, so the derivative of the function. So we're going to replace this with f prime of x sub I star, and we're going to square it. Okay, so we got that. Now, let's use the mean value theorem again. Because f of x is continuous, we can use the intermediate value theorem. Okay, remember the intermediate value theorem says that there has to be a point within the subinterval where the function is equal to 1/2 the sum of the two functions. So let's call it x sub star double star. So there has to be some value in the interval, right, within the interval, such that oh right, f of star star, so there has to be some star where f of star star, x of star star is equal to 1/2 f of x of I plus f of x of I. Okay? And that's by the intermediate value theorem. So let me okay. So the intermediate value theorem says there has to be some point within the interval that is 1/2 the sum of these two functions. Now, we don't, and that's because this is continuous. Okay, so we're assuming a continuous curve, right? That's one of the, remember, a differentiable curve. So, now we only have this right here. Well, if I want to replace this, why don't I just multiply both sides by 2? And now I get 2 times this is equal to that. And so now I can substitute that in. So now I'm going to substitute in this for this, which is now going to be pi times let me do it this way for the time being. Pi times 2 f of x sub I star star delta x 1 plus f prime of x sub I single star quantity squared and that's what I have so far. So now we can use this to approximate the surface area by using the summation. So now S equals the summation from I equals 1 to n of this thing. So now I'm going to rearrange some things. So I'm going to say 2 pi times f of x sub I star star times 1 plus f prime of x sub I star squared times delta x. And that's what I have. Now, that gives me the approximate surface area. Now, it almost looks like a Riemann sum, except we're evaluating the function at 2 different points. Over the same interval. Okay, so how are we going to do that? Now, although we don't examine the details here, it turns out that because f of x is smooth, if we let n approach infinity, the limit works the same as a Riemann sum, even with the 2 different evaluation points. Now, this makes sense intuitively because both x sub I star and x sub I double star are going to be in the interval. And so as n approaches infinity, they're going to approach the same value. So intuitively, it's not going to matter, right? Because if you're going to make subintervals smaller and smaller and smaller, eventually these 2 points are going to end up approaching x. And so it works. So if we take the limit, right? So S, we'll say this is approximate, equals the limit as n approaches infinity of the summation of I equals 1 to n of 2 pi times f of x double star times 1 plus f prime of x sub I star squared delta x. Well, what's going to happen? Well, the same thing that usually happens every time we do these, and we're going to change things to integrals and then dx. And so this is what we get for our final formula. Let's put it down here. So this is going to give us the integral. And now I'm going to erase all this because we don't need it. Served its purpose. And we get the integral from a to b of 2 pi f of x times 1 plus f prime of x quantity squared dx. And this is the formula, the integral that we're going to use to calculate the surface area, the area of a surface of rotation. Now, as with arc length, we can conduct a similar development for functions of y to get a formula for the surface area of surfaces of rotations about the y-axis. Now, so what I'm going to do is in the next video, we're going to summarize these in a theorem. Okay, so I could go through the same thing to derive a similar formula if we were going to go rotating around the y-axis. Okay, so in the next video I'll go through the theorem, I'll write out the theorem and I'll go over the theorem and then we'll do some examples. But this is the end result of surface area. Okay? And that's it. Have a great day.